We're good? I think so.
Yeah, I think so.
Okay. Okay, let's get started. Hello, everyone. Today is our second seminar talk here, and I'm happy to introduce our today's speaker, Nick. Nick now is a final year PhD student at Wisconsin Madison and also worked with Professor Fred Sella. Nick's research is broadly to understand like improving large foundation model. For example, like how can they scale, how can they train efficiently, and how can we adapt them to new domains, for example, like scientific ones. And Nick also spent times to do many of the good internship across like Meta on Llama team and also Microsoft Research to get AI on topics about like scaling all. And today he's going to bring many of the new recent work that he does, and we're happy to have him. And so everyone, please join me to welcome Nick.
Thank you so much, Brian. I'll go ahead and share my screen here. Um, okay. Can everyone see my slides?
I can see your slides.
All right, sweet. Um, cool. Yeah. Once again, thank you so much, Brian, for the very, very flattering introduction. Today I'll be talking about some work that I did over the past year on combining sort of chinchilla style scaling laws with LLM skills. And this was work done during an internship with the Llama team back when that still existed. Um, cool. So let's get started here. So yeah, as Brian said, this is kind of a recap, I guess, is a little bit of background on me. So as Brian said, I'm a final year PhD student with Fred. We're lab mates in the Sprocket lab here at UW-Madison, and my work sort of spans three sort of axes over the course of my PhD. One of which is what I've been calling sort of a science of foundation model scaling laws. And you'll kind of see like one example of what I sort of mean about that today. The second axis is data for efficient training and adaptation of foundation models. And that's something that our lab in general works on quite a bit. And then third, adapting these advancements that we've developed for foundation models to different scientific domains that are well beyond kind of the standard things that people use, beyond things like coding and math. Um, so. Um, so yeah, before I dive too deeply into this stuff, I wanted to kind of give all of you sort of a background on the kind of scaling laws that I'm going to be talking about today and kind of why they're important for foundation model development. So scaling laws can help forecast the influence of different training decisions that we make in the foundation model development pipeline and how these training decisions will impact performance as we scale up. And this is not a very new idea. So this is something that came about even before foundation models were really a thing, actually way before. So one of the earliest examples of this is from this 1993 paper from Carina Cortez et al. That tried to model sort of model error versus training set size as sort of like this power law sort of scaling. Okay. And then much later, OpenAI proposed sort of a scaling law for actual large language model foundation model training. And the idea here is that um, also as a power law, loss would go down as you use more compute to train your model, right? And so here we see like a bunch of different training curves, and if you like plot them all on the same plot, and you trace out in this black line here the sort of like envelope of these training curves, this like follows sort of a power law function. And basically the statement here is that like um, the reason you would plot multiple curves is you want to understand sort of the trade-off of like at what point would you be better off using your compute training a larger model, for instance, or something of that sort. Now, uh, I'm going to go into a bit more motivation about what I actually mean about sort of um, the science of scaling laws. And then after that, I'll dive into this scaling laws for skills, knowledge and reasoning skills work that I did at Meta. And then after that, I have a couple of slides kind of uh, at a high level talking about some of our ongoing work on scaling laws. And then yeah, we can open it up for questions after that. Cool. Um, so the problem that scaling laws solve is this. You have some compute budget measured in flops, so floating point operations, and you want to understand sort of how to use that compute budget. Suppose, suddenly your company is, opening a new state-of-the-art data center, and your specific lab has like, a budget of being able to use, let's say, like $5 million in like compute, and your company says, okay, like go train like a new model or something like that for us. So you want to understand sort of like what the exact sort of correct training decisions you should make. So what size of a model you should use, how much data you should use to train it, and various other things. How do you allocate this budget across the foundation model development pipeline so that you're optimally producing the best kind of model that you can with your limited budget? Okay. And so, as identified in sort of prior work, there are kind of two obvious choices here. You can increase the size of your model, so that's going to use more budget because passing data through a larger model costs more in flops, right? Because you have to do more operations with your larger parameter counts. Similarly, as you increase the amount of training data, that also uses up some of your budget, right? Because uh, of course, as you get more data, you have to do more forward and backward passes through your model. Okay. Um, and sort of the solution that was proposed to figuring out how to balance these two quantities is this idea introduced by DeepMind called chinchilla scaling. And what this gives us is some like notion of like compute optimality here. And so you can trade off the size of your model and the size of your data set to get sort of like some nice trade-off that gives you a lower loss compared to like overtraining very, very small model on a ton of data or undertraining a very, very large model. There's sort of a sweet spot in between, and that's called the compute optimum. And here in these plots, these are called isoflop curves. This was introduced in the Chinchilla paper. And the reason you have these sort of like hyperbolic shapes here is that each of these hyperbolas gives us a compute scale, and this is a compute budget. And so if you pick one of these, any point on this curve is going to be uh, some trade-off between the model size and the data set size subject to a certain budget. And so as you increase the size of your model, you have to decrease the size of your training data set and vice versa. As you increase the size of your data set, you have to decrease the size of your model proportionally to respect the budget. And so when you plot this across different budgets, the optimal point of each of these hyperbolas follows a power law, just as we saw before. Okay, and so this is called compute optimal scaling. And this is the type of scaling law that we're going to be talking about today. Yeah, and so popping up a level, we basically want to trade off the model size and the data set size to optimize your loss. Usually this is some validation loss, some held out set that's like usually IID with your pre-training set. You want to optimize this loss given your budget. Okay. Okay. Um, so I guess before I move on, are there any questions about this? Do we pause for questions in between, or is it after?
I haven't seen any questions now for on the chat, so maybe we can keep going.
Okay.
I think it should be okay.
Sounds great. Okay, I'll just keep going. Yeah, so now that we have sort of the basics covered, I want to kind of go over what I mean by this science of scaling laws, because I kind of introduced this weird term a few slides ago, and I didn't really explain it. So Um, Here's what I mean by that. So scaling law research is mostly siloed in industry labs that have a lot of compute. So if you sort of reason about these plots, you might sort of figure out that, okay, each of these points on these curves is a separate independent model pre-training run. And so it can be very, very expensive to reproduce the kinds of scaling curves that we saw, say, in the chinchilla paper. And uh, and even within these populations of models, these scaling laws are usually used to forecast sort of these like training decisions at like much larger scales. And so industry tends to have like a focus on scaling up. And arguably, this can miss many of the interesting scientific questions within the population of models itself. And here's kind of what I mean by that. And yeah, so these purple points here, you can think of these as sort of the compute optima of the scaling curves that I showed you before. And in industry, what researchers usually do is they fit this power law curve, and then they say, okay, now that we've fit this like scaling model, we want to understand what we can do if we max out our compute resources, if we use our entire data center. Okay. And so industry usually cares about this sort of like forecasted point that's way, way higher on this flop scale. So if you think of like the Llama 3 models, for instance, the Llama team might have like created a scaling population to forecast how what their training decisions should be for their Llama 405B model, for instance, which was their largest at the time. Okay. Um, but what I mean about the science of scaling laws is that I think there is still a lot of interesting scientific questions about the populations of models themselves. And so I would argue that even though industry uses these scaling populations as sort of a forecasting tool, I view them as sort of an observational tool for us to understand more about model development itself. And here are some of the examples of interesting scientific questions that come to mind for me. So one of which is whether or not different skills might evolve differently with scale. And so this is something I'll talk about a lot more today. Next is how other variables like, for example, the ratio of pre-training versus post-training might affect scaling behavior for different skills. And finally, how scaling law research can be done much more cheaply. So even though this, population of models is usually like much smaller than the larger forecasted model, it's still nonetheless often too expensive for academics to train a population of these scaling models to actually do this sort of scientific research for scaling law stuff. And so again, this type of work is often very confined to industry, and it's used as sort of an engineering tool rather than a scientific tool. And so over the past year, I've been working on many of these related questions. Okay, so if there are no questions, I'm going to move on to telling you folks about the different scaling behaviors of knowledge and reasoning skills. Okay, so our first research question in this work is whether the compute optima that I talked about before are dependent on the different skills that you measure. Okay. And so before we get into that, we first need to sort of understand what we really mean by a skill in this context. So informally, we say that a data set quantifies a skill if performance under some metric correlates with a model's ability to perform a task requiring the skill. So that's kind of like an informal variant of something that we've seen in some of our prior work, for instance, Skillet, in which we sort of define a skill as a data source. Here, we're saying that a skill is sort of a model capability of some sort that's measured using maybe some downstream task. I think there was a question.
Yes, there was a question about about how are hyperparameter chosen in these studies, like
Ah,
the training configuration stuff.
yeah. That's a great question. Okay, so oftentimes with scaling populations, there's been a couple of papers that kind of study like how the choice of hyperparameters influences things. And I think it's a little bit unclear. I think the ideal thing is that every single model on like a chinchilla curve is trained independently with its own learning rate schedule. And ideally, it should also be hyperparameter tuned. Now, that's very, very, very expensive. And so oftentimes even industry labs, they take shortcuts there. So um, yeah. I think one of the key things is that you want to have mostly independent training runs. And so if we go back to these chinchilla plots over here, you see that on this plot on the left, you have model size as the x-axis. And you might think, okay, well, different points on the same like vertical slice here might correspond to like intermediate training runs. But what industry usually does is they actually train like separate runs um, because like there are like sort of effects from like the learning rate schedule and things like that. Usually it's a cosine schedule. But yeah, that's kind of I would say it's unclear. Yeah, as of now. Yeah. Okay. Any other questions?
Nope. You can keep going.
All right, cool. Yeah, so we're talking about what a skill is. Under this sort of like informal definition, multiple different data sets can be associated with the same skill. And so you might think of different coding data sets, and different coding data sets would correspond to the same sort of coding skill, the model's capability to produce and generate code. Um, on the other hand, multiple skills can be quantified by the same data set. And so an example that I really like of this might be something like the abstract algebra portion of MMLU. Um, and I would argue that abstract algebra requires both knowledge skills because you have to have sort of the knowledge of the abstract algebra terms that you're manipulating, and also reasoning skills, mathematical reasoning skills, where you can actually manipulate the terms. Um, yeah. Okay. So, so to get a bit more concrete on our question here, we want to understand specifically if these two different knowledge or reasoning skills scale differently. And here's kind of what we use to measure these. And so as a proxy for knowledge, we used several knowledge-based question and answering tasks to sort of measure knowledge skills of these models. And on the other hand, as a proxy for reasoning, we used several coding benchmarks to measure the coding skills of these models. Okay. And here we split these different knowledge and reasoning skills into a hypothesis and a held out set. And what we did is we didn't look at the held out set until after we wrote the paper, and we did our entire analysis on the sort of like hypothesis split of these knowledge-based question and answering tasks and coding tasks. And then when we finally reported the results in the paper, we gave all of the results on the held out tasks. Okay. Okay. So here's kind of the main result. The question here is, again, if these compute optima from chinchilla-style scaling are dependent on the different skills that you measure. In other words, are they dependent on whether you measure coding capabilities or knowledge-based question and answering capabilities? And here's kind of the setup for this. We first evaluate the scaling checkpoints on the typical validation set. And so this is something that you might think of as a standard sort of pre-training style validation set, right? That you use to measure whether or not the pre-training loss is going down when you're pre-training. And that's going to give us the black line in both of these plots right here. Okay. And this is just standard scaling. The second step is that we evaluate these same scaling checkpoints on these different knowledge and code data sets that I showed you just before. Okay. And the compute optima for these are going to give us the red lines here. Okay. Um, and we see for knowledge that the compute optima for these knowledge skills in red is shifted over towards larger parameter counts compared to the black curve, which is standard scaling. Okay. And so we say that knowledge skills tend to prefer larger models. Now, if we look at the middle plot for code, we actually see the opposite effect, where these compute optima are shifted over towards smaller models, which are trained on more data. Okay. Um, and so that gives us our step three, which is we want to see how these compute optima shift for these skills compared to if we were to just do scaling on the validation set. Okay. Um, and so the kind of main result here is that indeed we say that knowledge skills tend to be capacity hungry, and these coding skills tend to be more data hungry. In other words, knowledge tends to favor larger models trained on less data, and code tends to favor smaller models trained on more data. Okay. All right. So I'm going to go into the second research question here, which I think follows somewhat naturally from this result, which is whether or not this is some kind of like confound of the actual like data mix that these models were trained on. Okay. Okay. And so as sort of a technical detail here, all of the pre-training checkpoints that we used for our scaling model were trained using the exact same data distribution. And so we roughly use the same proportions from different data sources. So our sampling procedure and training procedure is exactly the same for all of them. I'll pause because I think there's a question.
Yeah. So Jachi also asked like he heard about like a saying or belief that the skills are generally learned during the pre-training,
Hmm.
while post-training just lists them. Do you agree with this? And how does this affect to the scaling of studies?
Yeah, I think that's a really, really fascinating question. Um, I think so. My understanding is that like uh, people kind of like say things like this on Twitter and stuff. I don't know that I've seen like a ton of like papers that like make these claims and have like a lot of evidence behind it. But um, but I think it's nonetheless probably true. And I think like this is one of the things that like we could study much more deeply if we were to say do sort of joint scaling laws across pre-training and post-training and looked at the different skills. Um, and I think it's a very reasonable hypothesis that that indeed pre-training sort of gives you knowledge. It gives you sort of like linguistic knowledge and maybe like terminology sort of knowledge, and then doing things like RL post-training might sort of like sharpen the probabilities of reasoning traces that could give you, you know, more complex sort of manipulation of these knowledge terms.
Okay.
Yeah. Cool. Okay, yeah. So all of the checkpoints here are trained using the same proportions from the different data sources. Um, and our sort of question here is if we were to change these proportions, so if we were to change the fraction of knowledge versus reasoning. Uh, oh, sorry, is there a question?
No, I don't think so.
Ah, okay.
Yeah.
Uh, um, yeah, if we change the proportions of knowledge and reasoning in the pre-training mix across all of these checkpoints, um, does this actually change the compute optima for these? So we want to understand if the proportion of knowledge and reasoning is sort of a confound here. And so we're going to sort of do an interventional sort of study. And next, we want to see if we actually introduce this intervention, can we influence this behavior so much that it changes our finding from the first part? In other words, does this reverse the location of the compute optima for knowledge and reasoning? Okay. So to the first question here, we found that indeed we were able to shift the compute optima for knowledge and code by increasing the amount of skill relevant data in the data mix. And the way that we sort of conducted this evaluation is we took the lowest compute scale, so the cheapest flop scale hyperbola, and we retrained all of the models along that curve with different sort of versions of the data mix, where we increased for the left plot, where we increased the amount of code relative to knowledge, and for the right plot, increased the amount of knowledge relative to code. And we found that in both cases, as we increased the amount of skill-specific data that was prevalent in the data mix, the compute optima for each skill shifted over towards favoring larger parameter counts. Okay, so we can answer the first question in the affirmative. So indeed, there is sort of a way to influence the location of compute optima using the data mix.
Can I ask, like,
Mhm.
if I look into the left figure, the first blue line equals to is in the same training run to the right one, the most green one, because they're 11% for the code and maybe like the other percent are all knowledge. Is it how I read this figure?
The same training run?
So 11% of the code there. So
Mhm,
the
mhm.
rest of like 89, they are like they are all knowledge data.
Oh, no. It's not. Yeah, the pre-training mix isn't just knowledge and
Oh,
reasoning. We
okay.
just took the slices that we identified as code
Yes.
and uh tagged them, and then like yeah, like there are a lot of other things that are maybe both knowledge and reasoning or neither in the data mix, but we sort of just ignored that.
I see.
So it's not one or the other.
I see.
Yeah.
Okay.
Yeah. Okay. Cool. So now we can jump to the second question here, which was, again, if we, now that we know that we can actually manipulate the location of these compute optima by doing data mixing, can we actually do this in such a way that it changes what we found in the first plot? Because if it's true that we can manipulate it at that level, then this would suggest that indeed this is some kind of artifact of the pre-training mix. But if we're unable to show that, then it would mean that this is potentially something that's more inherent to knowledge and reasoning, perhaps. And indeed, it seemed like no, we were not able to show this. And this was because if we plot the proportion of skill relevant data against the compute optimal parameter counts for knowledge and code here, we found that the knowledge compute optima tended to shift at a much faster rate than reasoning. And so even though we were able to change the locations of these two compute optima, the knowledge one sort of always outpaced the reasoning one. And so it seemed like this was not, in some sense, an artifact of the pre-training data mix. Okay. Okay. So now that we've gone through these first two research questions here, we're coming up on this third one, which is sort of what the practical impact might be here. So we want to also understand how this finding would impact how practitioners and industry, for instance, might want to actually do large language model training. Okay. Okay. So we have sort of two sub-questions here. The first is if we can do some kind of data selection to bring the compute optima for these two closer together, even though this will perhaps trade off the capabilities of knowledge and reasoning. And second, we wanted to address sort of like a question that comes up a lot in industry, which is if your validation set that you're using for your scaling population accidentally quantifies skills that you don't want your model to have. Okay, so we're going to jump into the first question first. Um, so we found that indeed we were able to do a kind of data selection in which we were able to align the knowledge and reasoning compute optima. Um, and we found that this ratio was roughly at about 2.1 to 1 times code to knowledge here. Um, and of course, this is a trade-off. And so as you as you improve in your model's coding capabilities, you sacrifice some performance on these knowledge tasks. And so at the end of the day, before you even start modeling, um, you should really like have a good understanding of sort of what skills you want your model to have. Like if you're developing a very code specific model, then your scaling curves should reflect validations that actually um, elicit that kind of behavior, and vice versa for knowledge.
So I have a questions on,
Mhm.
so here, all of the validation set are the fixed one, are the same one. And they're all for, all of these validation data set.
Yeah,
Yeah, they are fixed one to test, right?
yeah.
Can you remind us where do they come from?
The yeah, yeah. So these are
At the beginning, right, there's a table about
yeah,
that
these
here.
ones. This is what you're
So
referring
we
to.
use all of these like set and also
Yeah.
they're going to be a fixed one to test all of them.
Oh, yeah. So yeah. So for knowledge and yeah.
Okay.
Again, for knowledge and code, like or knowledge and reasoning, these are the data sets that we're using
I see.
to measure performance. And so we're just measuring the negative log likelihood of the actual answer
Mhm.
here.
I see.
Um, yeah. So right. Another more subtle point that I wanted to point out is that here in these plots, I show sort of an average across all of the knowledge tasks and all of the code tasks, but it doesn't actually need to be an average. We actually saw this exact same behavior like separately on each individual task as
I see.
well. So I'm just showing it as an average just because it's convenient for plotting. Yeah. Um, okay. Cool. Any other questions about that? Okay, awesome. Um, cool. So next, I wanted to talk about sort of if your validation set that you're using for your scaling population quantifies the wrong skills. And so, for instance, a lot of uh, companies that train large language models, their kind of standard practice is to use perhaps their internal code base as their scaling validation set. And the reason they do this is because it's not their internal code is private, and so it's not something that would appear on the internet. And so they know that for sure it's not contaminated, or their training set is not contaminated with their validation set, right? Um, but our results suggest that if your validation set quantifies reasoning when you meant to quantify, um, something like knowledge or pre-training style data more broadly, that this can bias your results. And so if your validation set is mismatched to the types of skills you actually want your model to have, then your scaling forecast could be off by up to 50%. And actually, like scaling and increasing the forecast doesn't completely fix this. And sometimes you can still be off by 10 to 15%. Um, yeah, I think there's a question.
Yep. So is there a reason for knowledge data that to have no much correlations to the reasoning data? And why not using knowledge data for coding and reasoning data for coding?
Yeah, I think that's an interesting point. I think I think it's generally hard to quantify knowledge versus reasoning because in some sense, these are very human skills, I would say. So these are sort of like human sort of labels that we impose upon like, a model's capabilities. And yeah, we mostly used knowledge-based question and answering versus coding specifically because those are sort of like, most humans would consider knowledge-based question and answering a knowledge task, and vice versa. Most humans would consider coding to be reasoning based. However, it is a good point. There is actually they're sort of competing, I would say, definitions for skills. There's you know what I just mentioned is sort of like human-based skills, but then there's also model skills that are more sort of latent to the model. And so if you think of, say, like agent skills or like Claude skills, those are skills that are sort of like more latent to the model's capabilities rather than something that's human imposed. And so, yeah, I know that some folks over at Princeton, for instance, work on model skills versus human skills. So. Okay. Um, cool. Yeah, so kind of the key takeaways here are that knowledge and reasoning we found uh, scale somewhat differently. Knowledge tends to prefer larger models, whereas reasoning prefers more data. Okay. This seems to be something that might be fundamental to knowledge versus reasoning and something that isn't seemingly explained by the composition of the data mix. And finally, your choice of validation set matters quite a bit because it could impact your scaling forecasts by 10, 15 to 50%. And so your overall modeling goal uh, should really impact how you actually do this type of study. In other words, you should scale differently if you want to produce a reasoning model, for instance. Okay. All right. Um, any questions before I go into the ongoing work? All right, cool. So I'll start talking about some of the stuff we've been working on more recently since this knowledge versus reasoning scaling work, and let's jump right into it. So, uh, so currently we've moved to this question of if we want to create, say, reasoning models, but we have a target inference budget. Um, One of the main critiques of chinchilla style scaling is that nobody really does this in practice for intermediate scale models. And so you might argue that you really only need to do this forecasting for your largest model, your like Llama 405B model, and that all of the intermediate models, your Llama 7DB or 8B, those are just going to be overtrained. And so you wouldn't really use chinchilla style scaling for those because usually you would pick some intermediate scale model for sort of a target inference budget if you know that, your model of a certain size is going to cost a certain amount to do inference with. You're just going to like pick that model size and then just train it for as long as you can if you're a company, right? And so implicitly, the decision that companies are making with these like intermediate scale models is that they're picking an inference budget and then they're just training on all of their data. Okay. Um, but uh, but this is only the case if you assume that you're only making a single inference call with your model. And so now, in the past couple of years, we've moved into this regime of doing things like test time scaling, where we like sample multiple outputs and then figure out which one we want to use, or we do sort of longer thinking traces or things like that. And that can change sort of your inference budget calculation. And so it's no longer just a function of the model size alone. And so, and so again, our question is, if we want to create a reasoning model with a target inference budget in light of test time scaling, can chinchilla scaling still tell us what to do? Um, and sort of our hypothesis here is that if we consider inference cost and test time scaling, um, scaling could tell us to train even smaller models for much longer. And so um, the hypothesis here, and also our preliminary evidence kind of tells us that if we adjust chinchilla style scaling to take into account test time scaling laws, then this might be some kind of like scaling justification for overtraining your models. Um, and so that's kind of a preview of kind of what we're working on. And hopefully this will be out pretty soon. Yeah. If you have any questions or comments about this stuff, feel free to ask now. Otherwise, here's my email and my website, and here's also the lab's website. Um, and I also just wanted to give a quick shout out to all of my amazing collaborators at Meta and in the Sprocket Lab, of course. Um, yeah, I guess we can open up the floor for questions.
Yeah, thanks, Nick. And is there any questions from the Zoom uh, online that we can send in the chat? I have a questions on page number 30.
30.
Yeah.
Okay.
Oh, this one. Can you for my understanding is um I don't quite understand the rate here, how we calculate for the knowledge and the code one. Can you just give a little bit description on this figure? How can we read from here?
Yeah, sure. So like we had in the previous plot here, each line, if you look at the legend, has like a percentage of the skill relevant data. And so the top blue line on the left has 11.08% code, right? And this is the proportion of skill relevant data for code. Okay. And that proportion increases. And for each of these curves, you have some red point, some compute optimum, right? And similarly for knowledge, you have the sort of skill specific proportion. For knowledge, so the first curve here would be this 21.95% knowledge curve. And that goes up to like 84.9. Okay. And so what we do is we take these two columns of percentages, right? These are the skill specific ones for knowledge and code. And we plot those against basically the locations of the red points. And so, yeah. And so the x-axis here, the proportion of skill relevant data for the red curve, that would mean the proportion of knowledge data. And for the green curve, that would be the proportion of code data. Okay. And the y-axis here is the compute optimal parameter count subject to that data mix decision.
Okay.
Yeah.
I see. Thanks.
Mm-hmm.
Okay. Any questions from the Zoom here? Okay, if no, that's thanks again to Nick for his today's great talk about all the scaling law stuff, and we're looking forward for the new and recent work that we're gonna show, including the TTS stuff. And thanks again, and we will see each of you 2 weeks later for May's talk soon. And thanks again.
Thanks.